Hello everyone. Welcome to this recorded lecture. So today there's not a live lecture because it's a holiday, but because we also started the semester a week late, it was kind of messing up the schedule a little bit. So I decided that I'll give a recorded lecture, and I'll try to keep it short to give you sort of the core information that you'll need to get started with the new project. And the main reason for that is because there's also a vacation coming up. The deadline is actually still a couple of weeks from now. But I wanted to make sure that you also had 2 project sessions in which you could actually get feedback from me. Yeah? So that's why I'm giving this a recorded lecture on a holiday. So what we're going to talk about today is the principle of orthogonal decomposition, which is really the first true reduced basis method in the sense that most people talk about this, even though model decomposition we've seen fits the bill quite well. So I'm first going to talk about some of the concepts that we introduced last lecture. And we'll see that that's also going to play a role actually for this first reduced basis method. So we began talking about parametric partial differential equations, and we said, well, that's really the type of problem that we want to address. Yeah, so we have some partial differential equation that depends on a parameter or a set of parameters. And we have various different ways of representing that or of writing the equations for that. I wrote 3 ways here. And in each of these cases, I'm already jumping straight into the discretized version, meaning that we have a very, very fine finite element mesh to solve these problems. And then we have a sort of a strong form on the left. We have our typical weak form in the middle, and we know for if the spaces are finite dimensional, such as for finite element methods, then we can actually extract direct matrix sets of equations from that. Yeah, so these are 3 equivalent formulations. And we see that each of these formulations, they depend on this parameter, this mu. Yeah? So it's either the differential operator L all the way on the right, and then the force on the right hand side, that both may depend on this parameter. In the middle equation we see that it pops up in the bilinear and the linear forms, and on the right we see that it pops up in the stiffness matrix and the force vector. And we saw this kind of application arises in many different fields of engineering and also beyond that. So we talked about multi-scale materials, we talked about design optimization. In both cases we are looking to find a solution to a partial differential equation where we want to alter a parameter of some sort, our design variables, and we want to get a rapid feedback of what the solution might look like. And that's exactly what a reduced basis method is for. Or we want to have some real-time feedback of a changing system, either because we want to play with the simulation on the fly, or because we have a machine that gets certain input and has to predict the state in the future. Yeah, so that would be a real-time application. So I've seen that this shows up in numerous ways, and our objective is to create a very cheap simulation of this that is still able to capture the details of the high fidelity simulation. Now, one key important factor in all that we're going to talk about here is that we assume that this parametric partial differential equation has this affine decomposability. Now we're able to write this partial differential equation as separate pieces, which each only in a multiplicative sense depend on the parameter states. And that other parts, namely the certain sections of the bilinear form, that they become independent of the parameter. Yeah? So that's stuff that we can pre-compute, and in each new parameter point we can reuse our bilinear form, or on the lower representation, the stiffness matrix associated to that bilinear form, so we can reuse that at every parameter point, and all we have to do is obtain the new multiplication factor for that, which is a function of our parameter points, yeah, theta. And the example that we saw last time was the linear elasticity equations, where we rewrote them to make use of the Lamé constants or the Lamé parameters. And then we saw that we exactly had this affine decomposability of the bilinear form. And if we want to supply a stiffness and a Poisson ratio, so the Young's modulus and a Poisson ratio, then we had this theta as being the Lamé parameters, which are a function of those parameters. And each of those is multiplied by a separate bilinear form or by a separate stiffness matrix in this sense. So this was very important for our analysis and also for making the simulation workflow be efficient. Now, despite that at each new parameter point we'll be able to compile the stiffness matrix and the force vector relatively rapidly because of this affine decomposability, solving that at this stage is still very, very expensive because we're still dealing with a finite element mesh that might have tens of millions of degrees of freedom. So just the solving step itself is still very expensive, and that's the part that we really want to address and make cheap as well. But nevertheless, we could hypothetically think that at each point we can get a solution to this problem by simply solving that very, very expensive finite element sets of equations. Yeah? So we could conceptually create a solution map that takes a parameter point in our parameter space, denoted with this P, and gives us a solution in our finite element space, UH. Yeah, so we have now a solution map. And here I'm again stressing that the way that we represent a finite element method, yeah, my mouse shows up, is as a sum of coefficients times basis functions. And for standard finite element methods, those basis functions might be hat functions, or there might be higher order polynomials in there, but they're very localized. And each of those basis functions, which is a function of space, is multiplied by one of the coefficients that we obtain from solving our sets of equations in matrix form. Yeah, so those coefficients correspond to the solution vector here. And right now, as we said, this n, number of degrees of freedom, the number of basis functions, is extremely large, making this very expensive. Now, before we talk about how to reduce our parameter space, or the solutions that we might obtain, the first thing we should talk about is if this is actually feasible. Can we do this? So that's the question that we tried to address last time. And we saw that there are a couple of facets to this question. So the general notion that we needed there was the solution manifold, which is the collection of all possible solutions. So that would be that solution map, phi, acting on the complete parameter space, all the possible parameters that we might consider. And we denote that set of solutions M, that is our solution manifold. Yeah, so in set notation we see here, these are all the possible solutions, all functions in the finite element space, well not all of them, namely the ones for which there exists, this is that exist symbol, there exists some parameter point, some parameter in our possible space of parameters, such that the solution map actually maps to that function. So this is not going to be all possible finite element solutions, it's going to be a subset of that, as denoted here. It's precisely the fact that that is a subset, that it is a reduced space, that we might consider trying to reduce that with the reduced basis method. And we saw that there's really two things that factor in there to say, is this possible or not? That is, that talks about the width of the solution manifold. Is this narrow? Is this wide? If it's wide, it's going to be very tricky or impossible to reduce this. And if it's narrow, then we have at least the feasibility of doing so. And the smoothness of this manifold, which talked about the efficiency of doing something like that. And for the width, we had an expression for the Kolmogorov n width, which takes, for some n-dimensional subspace, it finds what is compared to that, what is the optimal subspace, and specifically the optimal width compared to that subspace. So if that is small, that means that we're able to create a very small error in this reduced space, in this subspace. So that is definitely a must. If that's not the case, then there's simply no way that a reduced basis method could ever work. And then the smoothness was about how sensitive is my solution, so this is these derivatives, with respect to a change in my parameter. And if that is a very high sensitivity, then creating a reduced basis method, all the small errors that we might introduce in just a finite element sense, the fact that we're not discretizing it exactly, but we're using these reduced bases, so all the error that has to move into our reduced basis method just by nature of the reducedness of the bases, that's going to have a huge impact on the effectiveness of the solution. And if this derivative is very small, that means that it's relatively stable and it's not going to have such a big impact. So in general, we want to have that this derivative with respect to the parameter is going to be small. And we see here actually a direct expression for that, where we find that the sensitivity of our solution with respect to the parameter depends on the sensitivity of each of the components of our affine decomposition with respect to that parameter, multiplied by that largest eigenvalue, which is a measure of the amplification, really, the amplification of that bilinear form. So to what extent can that bilinear form amplify that factor? There we go. We have something for the right-hand side. That was this guy, so those were all the forces. And we have something similar also for the bilinear forms. Those are these guys. And then we sort of have a normalization, which relates the amplification of the linear form to the smallest eigenvalue of the bilinear form. And then we have another sensitivity up front. Yeah? So these coefficients c and lambda, they in a sense reflect the sensitivity of the partial differential equation, or the different pieces of the partial differential equation, and these d theta, d mu's, they represent how sensitive is really any of our parameterized partial differential equations with respect to the parameter. Okay, so these were some new concepts that we talked about, and we had some graphical representation of that as well, so I'll rehearse that a little bit to give you, again, a feeling of what we talked about. And these might be a couple of solution manifolds that I'm going to show right now. And this is only a 2-degree of freedom system. Yeah? So we have to mentally extend this to a 1,000,000 degree of freedom or 10 million degree of freedom space. I'm in 2D, I can draw this. So it would only be 2 degrees of freedom, and the green line shows all the possible solution states of our parameterized partial differential equation. So that is our solution manifold. And well, the only way that we can reduce a 2-degree of freedom system anymore is into a 1-degree of freedom system. So we're looking for a one-dimensional subspace of a plane, which is a line. So we're looking for a line that represents our solution manifold well. And it's clear from this picture, well, there is no line that I can draw that is going to represent each point on this manifold well. And that's because the Kolmogorov n-width here is large. The minimal error that I will make is always large, irrespective of what line I might draw, what subspace I might draw. So then the next natural question is to say, well, what if this would just shrink and we would get something like that? What can you say about that? And it's true that maybe the Kolmogorov n-width is small. The error with respect to any subspace might be small, certainly smaller than the one on the left. But there's not one line in particular that is better than the other ones, and no matter what line we draw, we will always make the same error. So it also doesn't make any sense to try and get a reduced basis method for something like that. So the things in terms of Kolmogorov n-width that we're looking for look something along these lines, right? So this is all the solution points, they lie on one axis, and that will be our reduced space, or potential reduced space. Now I still draw a cross here because this is still not entirely what we're looking for, and that is because well, this is not a very smooth manifold, as you can already see on the lower left corner, where the solution depends rapidly on the parameter. And then one of the things that I tried to emphasize last time as well is that it's really not only that kind of wiggles that are an issue, it is also potentially what is going on in the rest of the domain, and it has to do simply with the spacing of our solutions with respect to the parameters. Yeah, so if I change my parameters and this goes up and down, well, clearly that's not very smooth. So the derivatives, and certainly the second derivatives, because I've only been talking about the first derivatives, but in a similar sense the second derivatives are important. So they're going to be very large here. But suppose that I still keep my change in parameters the same magnitude, and suddenly it starts to behave like this. And this looks very smooth, but clearly my solution jumps a lot from parameter to parameter, which still illustrates that this is not a very smooth manifold. Also on the remaining width of that line. So what are we looking for? What are we happy with? Well, that would be something like this. Clearly I can create a subspace, a one-dimensional subspace, which would be a line that looks something like that. And each point in my manifold is, well, relatively well represented by a point on my subspace. So my Kolmogorov n-width is small. Yeah, the maximum error that I'm making, which might be something like that, right? That would be my Kolmogorov n-width. So that's small. And this is smooth. Well, I'm saying that, but really in order to make that claim, I would have to consider each of the points and change my parameter by the same step each time and see how my solution changes. And if that changes something like this, then this would be smooth. Yeah? So if there would still be large jumps in terms of solution, then this would not be smooth. So I should really say this in connection with the dots that you're seeing right now. Okay, this was still very hypothetical, and it's trying to answer the question, can we do what we want to do? And it's not really yet about how do we do what we want to do, namely how do we get that reduced space? How do we get that space that is a subspace of our finite element space that represents every possible solution quite well? So what we're trying to find is this red line, given this green line. And by looking at it, it's quite obvious what we want to do. We want to draw the line that I just drew. And obviously that's physically intuitive, but how would you computationally do this? Well, in a two-dimensional set of equations, or a two-dimensional system, this might actually also... oh, I'm jumping ahead. Wait. Did I? I'll first do this one. Yeah, so how do we do that? Well, in a two-dimensional system, you might actually already have an idea of tackling this problem, because suppose that I have a bunch of points. So instead of having this complete solution map, which will be very expensive to compute, I just take a bunch of samples. And so I'm computing phi at a whole bunch of locations in my parameter space. And by doing so, I get sort of a discrete representation of our solution manifold. So I'm no longer looking at the green line. I can't see that green line unless I compute it for tons and tons of points. And even then I still have no guarantee that that is the line. So we're going to just sample a bunch of points and get a representation of our solution manifold. So how, from these points, would I now obtain the line that I'm looking for, which clearly looks something like that? Well, I don't know if you're thinking along here, but I would say the quite obvious answer to this would be a least squares kind of approach. We're trying to find the line that approximates each of these points in red that I just drew in a least squares sense. So how would we go about doing that? Well, you would create a matrix which has each of these points in here. So this is x and that is y. So this will be point 1, point 2, point 3, etc. And for each point I have a solution. x1, y1, x2, y2. And we're going to do this for all points that I drew here and the number of points. So what we're going to do is we're going to call each of these possible solutions a snapshot, because I've solved a finite element system of equations for one parameter point in our parameter domain. It gives me a valid solution. I'm going to call that a snapshot. So each of these points are snapshots. So, and looping all the way across, we end up with ns of these points. So that's the number of snapshots. So we're going to do this all the way until x and s and y and s. So these are the number of snapshots. And each of these points corresponds to one of those. Yeah? So each of those is a snapshot. Now I should be maybe a bit more careful here. Call it like that. Okay. So I have a matrix of snapshots, and well, naturally we call this matrix the snapshot matrix. We have a letter for that, typically we use S, so this is the snapshot matrix. And our objective right now is to create this Vn, and n in this Vn, remember that was the degrees of freedom or the dimensionality of that reduced space. Well, clearly the only way that we can reduce a two-dimensional space any further is if we talk about a one-dimensional space. So this is going to be V1. So we're looking for this space V1, which is spanned, well, it's one-dimensional, so it's spanned only by a single vector, which we'll call x tilde, y tilde. Yeah, so this is this space, which is any linear combinations of this one vector, which represents a line. And we're looking for exactly that x tilde and that y tilde such that the error that we're making with respect to any point in our snapshot matrix, any snapshot in our snapshot matrix, is minimized. So we're looking for x tilde, y tilde, such that, and the way that we could talk about this is that the sum going from I is equal to 1 to, well, ns, the number of snapshots, of the error in terms of a least square, which of course we measure as the magnitude of the difference between each of these points, minus a, so it's a linear combination of any of the bases in the span, yi minus a y. So that is minimized for some, and for each point we have a new a. Somehow I didn't write it in my notes, so that's why I'm a little bit confused right now. And we're measuring that error in Euclidean norm, right? So for each new space we have to think about a new way of measuring lengths. So we have a new norm for each space. Well, these are still the vector spaces that we used to, so we're doing the Euclidean norm. So for some a. Okay. Well, I'm not going to talk about the algorithm of how you would obtain a least square solution to something like this, because I want to talk about something that is more general. Yeah, I can do this for one line given a certain number of points, and that will give me the least squares regression. But that is not really relevant to the case that we're interested in. In our case, our snapshot matrix is going to consist of finite element solutions, which each might be 100 million degrees of freedom. Yeah, so then we have columns that are 100 million degrees of freedom or 10 million degrees of freedom in length. And we might have 1,000 snapshots or something like that. And we're not looking for V1, the one-dimensional space that represents each solution state best. No, we might be looking for V10. So we use 10 reduced bases. Or if that doesn't work, maybe V100. Yeah, solving a 100 degree of freedom system is still going to be much more expensive than trying to solve that old 10 million degree of freedom system over and over again. So depending on the problem that we're looking at a certain way of, or a certain extent to which we want to reduce the space. But for sure we typically are not looking for a one-dimensional system. Yeah, so something like the least squares, I'm sure that there's a generalization for something like that. But we're going to talk about a very specific case of doing this, and that's the singular value decomposition. So just to make a point here, what we're looking to do is so more generally, we have a snapshot matrix S that lies in our, well, how many of these are there? Well, there's going to be this big N number of degrees of freedom. So here that big N is 2. We have 2 degrees of freedom, but it might be 10 million times NS, the number of snapshots. So it might be 1,000 or something like that. So that is typically the snapshot matrix that we're looking at, and we're looking for a space Vn, where n is typically really not 1, as is the case for the linear or the least squares problem that I was addressing earlier, as the span of not a single vector, but now n vectors. So n1 tilde, n2 tilde, going all the way to n small n, where each of these vectors is a vector in our big N. So we're looking for an n-dimensional subspace of our finite element space, which is our big N, at least in the matrix or in the vector notation. And we're looking for that in such a way that it has sort of this least squares nature to it, that each point in our snapshot matrix is really well represented by some linear combination of our vectors. Okay, now I skipped a slide. I think I will keep on skipping that to the end of the talk that I want to give today. So I'm going to focus first on this problem. And as I said, the approach that we're going to take here is well, singular value decomposition, and an acronym for that is SVD. So we have here SVD/POD, and that's because POD, principal orthogonal decomposition, is the reduced basis strategy that makes use of a singular value decomposition to obtain those bases. Okay, so what is SVD? Well, SVD singular value decomposition. Oh, singular value decomposition. Is a matrix decomposition. Now, what is a matrix decomposition? I suspect that during your studies you've actually come across many different types of matrix decompositions. So just to put this in the right context, I want to give a couple of examples of what matrix decomposition are. So we have matrix decompositions like, suppose that we have some matrix A. Well, one of them that you might have come across during linear algebra is the LU factorization, where my matrix L is some lower diagonal matrix that might look something like that, and the matrix U is an upper diagonal matrix. It might look something like that. So we have rewritten our matrix A into a decomposition of submatrices, other matrices, and this is supposed to give us some sort of information in whatever form. Yeah, so this is typically used for actually solving systems of equations, because now the inversion step becomes much more effective. Yeah, so this is a decomposition that is useful in linear algebra for solving matrix system of equations. Now, what is another one? We might decompose a matrix A into Q, a Q, and an R. So this is the QR decomposition, where Q is an orthogonal matrix, or orthonormal, I should say. What does it mean for a matrix to be orthonormal again? Well, that meant that the inverse of Q is its own transpose. And so if I multiply Q by Q transpose, or Q transpose by Q, then I would get the identity matrix. So these typically are rotations. So that means that every single column and every single row in this matrix is, well, first of all, linearly independent with respect to the other ones. It is of unit length, and it is orthogonal to each of the other rows / columns. So QR decomposition, so maybe I'll say this, typically we say LU factorization, and QR decomposition has a Q and now a right upper diagonal matrix, which again looks something like that. And this decomposition is useful again in linear algebra for solving. Often they use something like this for eigenvalue, to get the eigenvalues and the eigenvectors. So we have algorithms that can do an LU factorization and a QR decomposition in an effective way, and then use those to solve problems like an eigenvalue problem or matrix vector multiplication problem, matrix inverse problem. Now these are from linear algebra to also give you sort of a physical interpretation. In continuum mechanics we often talk about a polar decomposition, and that is a multiplication with a rotation matrix R and some stretch matrix U. And we could do then the right or the left version of that. So we could also first stretch and then rotate, and we often did this for certain tensors. Yeah, so this is a rotation and a stretch. And this gave us an insight in the way that these tensors work. Yeah, so the point that I'm making here is that there is multiple ways of factoring, decomposing a matrix in different matrices that somehow give us insight in what this matrix is telling us. And the last one that I'll address, because that's one I'll actually also need for the next lecture, will be the spectral decomposition. So this was the polar decomposition, and this is a spectral decomposition, But we're going to write our matrix as a matrix V times a diagonal matrix times the inverse of V, where in V, the V are the matrix of eigenvectors multiplied by, and this is sorry, the inverse, multiplied by a diagonal matrix of eigenvalues multiplied by those eigenvectors inverse. And the special property of symmetric matrices, so this is general, and specifically for symmetric matrices, it turns out that each of the eigenvectors are orthogonal with respect to each other, and then we can use this property, because each of the, and we can also normalize them, so we can actually write this now in a slightly easier way, like that. Yeah, so the inverse of the vector or the matrix of eigenvectors is going to be its own transpose, because it's orthogonal. So this is specifically the case if A is symmetric. Okay, so a whole bunch of different decompositions, and I haven't addressed SVD yet. The point I'm trying to make is, well, there's a couple of ways of decomposing matrices. None of these it just depends on the situation that we're looking at, what we find interesting. Most of the times these actually exist. I'm not sure what the conditions are for each one of these, but a very important point here is that they typically focus on square matrices. So typically, pretty much any one of these typically focuses or has its strength when it comes to square matrices. And for the spectral decomposition and the polar decomposition, that is definitely true, because tensors are always square, and the eigenvalues and eigenvectors also make sense if we're talking about square matrices. So for those, we really only have those decompositions if we're talking about square matrices. And also LU and QR, well, they only really make sense if we're talking about square matrices. Well, square matrices, they occur all the time in physics and in data science. But right now we're talking about a matrix, the snapshot matrix, which is not square. And also in data science, there's also many cases in which we're talking about matrices that are not square. Any kind of data sampling typically does not result in a square matrix. We never have the amount of states equal to the amount of samples. And that's really what we're seeing right now as well. So we're looking for a different decomposition approach that gives us insight about the matrix that actually functions and focuses maybe even on non-square matrices. And that is exactly what the SVD is. So the SVD applies also for non-square matrices. Now, what is the singular value decomposition? Well, it's a decomposition just like the ones that we saw. It is a decomposition of the matrix, and I'll jump right into our snapshot matrix S as a matrix U multiplied by a matrix sigma multiplied by a matrix Z transpose, where the matrix sigma is diagonal and decreasing, and what I mean by decreasing is that, well, it's diagonal and each subsequent diagonal value is smaller than or equal to the previous one. And that's just a matter of shuffling, so that's a convention. And these guys are orthonormal matrices. Which means that if I multiply U by its own transpose, I get the identity, and the same thing for Z. So what can we say about the sizes of these matrices? Well, first we have a snapshot matrix that is big N times number of snapshots, which means that we have to start with the matrix multiplication that has a big N, and we have to end with one that is of size ns. Well, for orthogonal matrices to make sense, these have to be square, so I have here times n, and here I have one that is ns times ns, which automatically means that the central matrix has to be n times ns. And that's kind of funny really to talk about a diagonal matrix that is not square. So what do I mean by that? I drew a couple of these also to give you sort of a physical interpretation of what this is. So this would, for example, be the shapes that we were looking at. Yeah? So we have a non-square matrix S, the snapshots, just like we had here. So it looks something like that. And then we have a square orthogonal matrix. We have a square orthogonal matrix all the way in the back. And we have a diagonal matrix in the center. And diagonal means that it only has values if its row and its column index are equal. Yeah? So only this red line is filled. And we have zeros everywhere else. Now this is actually not typically the case that we're interested in. This is not the typical matrix size that we're interested in, even though that was the case here, because we only had very few degrees of freedom. Normally we have many degrees of freedom, and we have actually fewer snapshots. So then it would look something like that. So that's typically the more relevant case to us. Where we have a very slender and tall matrix of snapshots, and then by drawing the same dimensions everywhere, we see that we now have a very large orthogonal matrix sitting up front. We have again a slender, tall matrix of diagonal values, and a small block matrix all the way in the back again. Okay, so this is just a decomposition. What am I trying to get at here? Why is this so interesting? So the matrices that we obtain here, the U and the Z, they are special in the sense that they exactly capture the most important parts of the rows / the columns of the snapshot matrix. And that sort of happens automatically by forcing a decomposition like so. And in the next lecture I'll actually go into a little bit more about how we create this decomposition. For now, so that you can use this in the project, I want to emphasize why we're interested in this. So again, the matrix U, which has the same number of rows as our snapshot matrix in both cases. That means that every column in this matrix is somehow an important part of all the columns of the original snapshot matrix. And because this is ordered in a decreasing way, it is exactly so that the first column in our U matrix is the most important column to represent any solution in our snapshot matrix. And the second column is going to be the second most important one. And in a similar sense, each of the rows in the Z matrix represents the importance of all the rows in the original snapshot matrix, where the first row is the most important one to represent all possible rows in our snapshot matrix. So how can we see this? And I can actually write this to give you an idea of why that is. And that we can actually see that by simply working out the matrix multiplication that we obtain if we decompose this matrix as such. Suppose that we have, well, the case that we were looking at was if we have 1,000,000 degrees of freedom and 1,000 snapshots. So again, a very tall, slender matrix. It is 1,000 times taller than its wide. So we're writing this as a square matrix N, which is now very big, right? It's going to be the largest dimension in both ways. Multiplied by that diagonal matrix that looked like this. And again, a square matrix that is as square as the smallest dimension. And what I said was, well, each of the columns here is going to be very important, and each of the rows here is going to be very important. And it's going to be important in a sequential sense. The first one is going to be most important, the second one is going to be second most important. Why is that? Okay, so I'm gonna write each of the columns here as xi. So we have xi1, xi2, going all the way to xi n, right? This is an n by n matrix. This is n and this is ns. So we have big N of those columns, each one being less and less important than the previous one. And here we have an ns by ns square matrix, and I'm going to call each of these zeta transpose, yeah, because there's still a transpose hidden in here. That's mostly a notational trick so that we can actually talk about each of these as a vector, making each row now a line vector. So we have zeta 1, etc., going to zeta ns. So what do I actually get? Oh, sorry, and I have now as our values here, sigma 1, sigma 2, going to sigma ns again. Yeah, okay. So what happens if I carry out this multiplication? Okay, suppose I first multiply the first matrix by the second matrix. So I'm taking the first, am I actually seeing this as I'm hovering over? Yeah, okay. So I'm taking the first row and I'm multiplying that by this first column. Well, that's going to be simply sigma 1 times the first value in xi. Now let me take the second row. Well, again, this is only going to be the xi component multiplied by sigma 1. And I can do this for every row, and I will only get sigma 1 times xi 1. Okay, so now I can do the same thing for multiplying by the second column. And I'll see that sigma 2 really only multiplies by xi 2. And so another way of writing this would be that I already contract both of these into a new matrix. So what is going to be the dimension of this matrix? Well, I have n to begin with, and I'll have this dimension here, ns, over here. So I'm going to have to fill this all in, so it's probably going to increase in width a little bit, but the idea here is that it has a small width right now. So what we would get sigma 1 times xi 1, sigma 2 times xi 2, all the way to sigma ns times xi ns. So what happens with all these vectors here? Well, they kind of disappear, yeah? Because each one of the multiplication of a row by a column, well, each one of these vectors here is always simply multiplied by a bunch of zeros. So in effect, all these vectors are actually useless. They are simply padding to make this matrix orthonormal. They are orthogonal with respect to each of the other ones. They're also each normal, but in a sense they're not reflective of what's going on in our snapshot matrix. And that's why in this slide they actually call these the filling matrices. So there's another singular value decomposition that's called either the thin SVD or the economy SVD that kind of already gets rid of those. But for a bunch of proofs, it's much nicer to work with orthonormal bases or orthonormal matrices. So that's why in the standard form we still have them. But as you can see, after one matrix multiplication, I've already killed all of those components, and this is really the matrix that we're dealing with. Yeah, so we have ns vectors, each of magnitude n, as a multiplication of our sigma multiplied by these vectors. Now I still have to multiply that by that square matrix that is ns by ns of zetas. Oh, that was not a zeta. Zeta transpose 1 going to zeta transpose ns. And how does this multiplication work? Well, I'll take the first row here, multiply by the first column. What do I see? Well, the first component of sigma 1 zeta xi 1 is multiplied by the first component of zeta 1. The first component of sigma 2 xi 2 is multiplied by the first component of zeta 2. Going all the way up until the end, where we have sigma ns, xi ns multiplied by zeta ns. So we see that each of the vectors that I have in my left matrix is really only connected to the same index number vector in the matrix Z of zetas. So what do we get? Well, I can actually write this now as a summation. I get a summation of I is equal to 1 to ns of these sigma values, sigma 1 or sigma I, of our psi vectors, psi I, multiplied by zeta vectors, transpose. How does this multiplication work? Well, I have n times 1 by 1 times ns. So each of these is actually a n by ns matrix. So I'm summing a whole bunch of matrices together. That's what this multiplication is doing. And each of these individual matrices that I'm summing, so what am I getting here? I'm getting a sum of sigmas multiplied by tall vectors multiplied by small vectors. Yeah, so I'm summing a bunch of matrices together. All of dimension n times ns. One more important thing to note here is that my original vectors psi and zeta, well, they're normal, so they have a magnitude of 1. So this whole matrix is composed out of vectors that really are of magnitude 1. So it's sort of a unit matrix by itself. And it is the sigmas that now carry the weight of each individual component of this series. And since we ordered our sigmas to be in a decreasing sense, it is the first sigma that has a matrix associated to it that carries a lot of the information from our snapshot matrix. And it is the second one that carries the second most information. And it's the last one that really doesn't carry much information at all. I could also throw that away. And that's exactly where the compression comes from. Yeah, so the compression comes from throwing away a whole bunch of the ones in the back that we're not interested in. The first one might be the first sigma might be a value of 1,000, and the last one might be 1 over 1,000. So there's a factor of 1,000,000 difference between the significance of the first block, the first matrix, which is composed out of these columns and these rows. And that carries a significance that is 1,000,000 times more than the ones all the way in the end. Okay, so yeah, so the terminology that we have for this is that these guys are the singular values of the matrix. They carry the weight of each of the individual xi's and zetas, and they are called, these are the left singular vectors. Left because they're from the matrix on the left. And these guys are the right singular vectors. Yeah, so that's why this is a singular value decomposition. So these are not yet eigenvalues and eigenvectors in the same sense that we had, we're very used to for square matrices. Actually, in the next lecture we'll see sort of a connection with that. But these are something else. They are singular vectors, singular values, and they represent, in a very strong sense, the data in that matrix. So this SVD is also hugely important for data analysis. This is precisely showing if you have a huge data set of images, and I'll actually talk about that more, then these are going to represent the important features in those images. So what is our objective right now from a reducer and modeling perspective? Well, what we want to do is we find a collection of bases, a collection of psi vectors that best represent the entire possible solution manifold, the entire snapshot matrix. And the way that we say that is that the best rank K approximation of our complete snapshot matrix S is going to be the sum, so this is going to be an approximation to S tilde, is going to be the sum of the first K of this series. Of the first K singular values multiplied by the first K singular left singular vectors times the first k left singular vectors transposed. Rank k, what does that mean again? Well, the rank, if something is full rank, then it has, in a sense, all the information that it can possibly capture. It's the rows span the complete space, the columns span the complete space. All rows and all columns are linearly independent. Well, for each of these components, that's clearly not the case, because each of the components within each of the series, well, it only depends on one vector and one column. So each of these guys are also rank 1. So we're summing a whole bunch of rank 1 matrices which carry only very little information by themselves in terms of what they span, but that represents a lot of the information from the matrix. And the best rank k approximation of the complete snapshot matrix is clearly then a sum of the first of these the k first of these rank 1 matrices and multiplied by the singular vectors, singular values. Now, what we're going to talk about more in the next lecture as well is that this already gives us, well, pretty direct representation of the error that we're making with our reduced order model. Because all the sigmas that we're not taking into account, so from k plus 1 until ns, well, they represent exactly the amount of error that we're making. And we have actually pretty strong theorems for something like that. There was rank 1, I'm not sure if my picture was over there. Okay, so this was the theory behind what we're doing. Let's try and make this conceptually clear by some examples. And, well, I think the first very clear example of this is image compression. So we have here a photo of the Leibniz University. And we could think of a photo as precisely a matrix, right? We have columns and we have rows. And in this case, the dimensions of my matrix are 765 by 383. So I have, and then actually multiplied by 3 because we have RGB. But we have a data matrix here that has a whole bunch of entries. Yeah, so this is going to be my snapshot matrix, my data matrix. And what I can do right now is I can do SVD on that data matrix, and I can simply do this in Matlab. There's a function for that, SVD, or in Python. I think I did this in Python. And I decompose my snapshot matrix or my data matrix in this U, the sigma, and the Z. And what I'll do is I'll only take the first vector and the first column, and I'll multiply these just in the way that this series is written out, and I'll get a reduced picture of this picture. Yeah? So if I do that for only one of these bases, I'll get this picture. Yeah? So this is already very clearly showing that this is a linear combination between, well, different rows here, which are each the same zeta, so this is zeta 1, and a column here, which is psi 1, and each new row and each new column is just a linear combination of those multiplied by the first singular value. Yeah, so this entire picture is nothing more than sigma 1 times psi 1 times zeta 1 transpose. So that is what you're seeing right now. This is only the first mode of my data matrix. And well, I could argue, well, we're already sort of seeing the basic features of the original picture, right? We see sort of the tower and the width and the grass. So in a sense, this is already kind of capturing the core information of our entire solution matrix. But clearly I can go a lot further. I don't have to do this only for the first mode. I can sum the first couple of modes. And if I sum the first 5 modes, then I already get a picture like that. Now, clearly this is not the same as the original picture, but given that I'm only using 5 modes, I would say this is already getting pretty accurate. And if you think about the amount of data that we're compressing by, instead of storing the entire array of data, we're only storing now 5 modes, which is just 5 column vectors and 5 row vectors multiplied by 5 numbers. Yeah, so in terms of storage, that's much cheaper. Well, what happens if I add more? This is after 20 modes, and clearly now we're already seeing the castle. If I go to 50 modes, I see something like this, and we see pretty much all the details right now. There's a lot of noise still, and if I use 100, then I already also get rid of a lot of the noise. Now there's still some noise going on, but considering that I'm replacing the entire photo, which was 800 by 400, by just 100 columns, we're getting quite a nice compression of this. And this is pretty much exactly what image compression is doing. I'm sure they do this smarter than that. But what I found funny is that when I did this, the kind of noise that you're seeing in the picture right now, it really reminded me of the noise that you get if you open a JPEG in Paint and you make some small edits, maybe you write something on there and you store it. Then you always have this funny grainy looking noise around the pixels that you added, or that you edited. And it's precisely because it's trying to recompress that now with only a finite number of modes, and this is the noise that you would see in a compression algorithm like that. So I'm not sure if they exactly use SVD, I suppose they use something slightly more specific to the task. But I think it's already illustrating really well the point that I'm trying to make. Yeah, and for a reduced basis method, this might already be way too detailed for us. We might be happy with something like this, or maybe even with something like that, right? In the sense that we're happy if our reduced basis method represents every possible solution state to this degree. And I'm sort of making this very difficult on our reduced basis method if I'm talking about it like this, because in a summation that we are interested in, a partial differential equation that depends on parameters, each possible solution state in our solution manifold, it's going to be relatively similar to the other ones, given that we are not dealing with something very extreme. Yeah, so each of the columns in our snapshot matrix, they will be in some sense similar to one another. And for a photo, that's clearly not the case. Every column is going to have completely different data. Yeah? So there's no correlation between the 50th column and the 500th column, right? Whereas for a snapshot matrix, for a partial differential equation with parameters, we might expect to see a whole bunch more correlation. Yeah, so the more relevant case really, and I'll talk about another example also involving pictures, is if each column in our data matrix sort of represents in some sense the same data. Yeah, so what I'll do next is I'll take all the photos from the IBM website and I'll restructure all these photos. These are all the people that work at the IBM. And I'll use each of these photos as one data column, which makes the number of snapshots equal to the number of photos. Yeah, so what I'm doing is I'm taking a picture, I'm stretching the data, the number of pixels, into one big lengthy column. So you would get something like this on the left. Okay, already kind of showing the clue here. So you would create now a snapshot matrix which has here the number of photos. So the number of photos. And each column includes the data of that picture. I do SVD, and the first column that I get, so this is the first xi, and this is the second xi, the third xi, fourth, and the fifth. Yeah? So these are again the columns from the U matrix. Restructured back into photos. So these are the first bases that we would use in a reduced basis method. They would look like this. Yeah? So this is the compression of a whole bunch of photos into the general photo features, the general facial features that we have. And I find it kind of interesting that even though these are clearly not faces, each one of them, we still kind of recognize people in here. And for the higher order modes, you actually get a whole bunch of more detail and you can sort of start to recognize some faces individually, and that is because the number of snapshots that I have, the number of photos, is relatively small. If I would also have 100 different photos, each of the different modes would be a very rough representation of a face, and each of the individual faces would be really well represented by a certain linear combination of the different individual singular faces here. Yeah? So these are the singular faces of the IBM. So these are two examples illustrating the use of singular value decomposition for images, and I hope that you can conceptually also apply this now to a partial differential equation. I'll also take one example from a book that actually directly applies to that. So here we have a parameterized partial differential equation where we have sort of a tube, and there's some fluid flow going through that tube. So they computed the fluid flow beforehand. And they're interested in the heat exchange here given different temperatures on these flanges. Yeah, so the parameters here, there's going to be 4 parameters, I believe. It's going to be the temperatures on gamma 1, gamma 2, and gamma 3. and it's going to be the diffusivity of the flow, or the heat diffusivity of the fluid. And they're interested in, suppose that I change the temperature, suppose that I change the diffusivity, how does the heat distribution, or maybe specifically the temperature on the outflow, how is that going to change with respect to that parameter? So they create the partial differential equation, they set up the finite element solver for that, they loop over a whole bunch of different parameter states to create their snapshot matrix, they do SVD, and they take only the first few solutions as the reduced basis modes. And this is what they obtain for something like that. Yeah? So these are, in the example before, these are the singular faces of all the different photos. These are the reduced basis, the singular vectors, the solution states corresponding to the first few columns in the singular value decomposition of the snapshot matrix. Yeah? And based on the theory that I showed you before, every solution, every possible solution in our snapshot is quite well represented by a linear combination of only these first few modes. Even though the snapshot matrix might have 1,000,000 degrees of freedom, we can represent each solution state quite well with only 6. And the extent to which they capture that quite well is captured by the singular values. And here we see how the singular values decrease with the number of bases. And we see that, well, I think this is normalized, so the first one is 1, and the last one are 10 to the minus 8. Yeah, so if I kill all the ones below here, if I don't take those into account, then I'm making an error that is of the order of 1 out of 1,000,000. If I kill all the ones below here, then I'm making errors of the order of 1%. And actually this goes with a square, so it's even better than that. I'll talk about that next lecture. So the idea is I'm only going to take this guy, that guy, and a bunch of these, and by only taking those into account, I'll still be able to represent every possible solution state really quite well. Okay, so those are the examples that I had that I wanted to talk about today. In general, the SVD. So the next thing I'll do is I'll talk about the project, and then I'll actually jump back to the slide that I skipped, because I think that illustrates really well in general what a reduced basis method should do, also in connection to the project. And I'll actually first do that slide, and I'll connect the project to that. Okay. Yeah. Okay, so this is the general idea of a reduced basis strategy, a reduced order model strategy for a parameterized partial differential equation. So the idea is that we have this separation of offline and online that I've addressed a couple of times. And we're very willing to pay computational expense during the offline phase of our solution strategy, as long as that means that we're able to quickly, rapidly, and cheaply produce solutions during some sort of online operational phase of our simulation workflow. Yeah, so we have this strict separation between online and offline. And the importance there is that during the online phase, I don't want to have to do anything that involves this large number of degrees of freedom. So we can actually, in every step of our procedure, we have to make sure that whatever operations we do that require operations of that magnitude of 10 million degrees of freedom, that they all fit in that offline phase, such that during the online phase, all operational cost is of the order of the magnitude of the reduced basis method, which is the small n, yeah? It might be 10. So that's a general idea, and the different inputs for these different phases. Well, first of all, the offline phase, so it has the parametric partial differential equation, including the parameter domain that we're interested in. Then we're going to do some pre-computation, such that during the online phase, all that we get, well, we get the information from the offline phase, so all kinds of pre-computed information, and we get a new parameter point, and with those two things, we want to quickly solve some sort of problem, probably just the solution state for that parameter point, to get some sort of output. And that has to be cheap. So what boxes fit into these different planes? Well, we talked about the affine decomposition. That's the first thing that we're going to do in the offline phase, and that's also the first thing I have to do for the new project. So we're going to decompose the parametric partial differential equation into multiple stiffness matrices and multiple force vectors that each are completely independent of the parameter point and only in a multiplicative sense sum up to be the true stiffness matrix for the parametric partial differential equation for that parameter point. Okay, so that's the first stage. So we need to conceptually do this, right? We need to write out how we would decompose this, and then secondly we have to implement the strategy for obtaining these individual stiffness matrices and force vectors. Then the second part is that we're going to explore the solution manifold. And there's different approaches to doing this. The one that we talked about today is the principle of orthogonal decomposition. So we're creating an array of snapshot matrices. We're doing singular value decomposition. And from our singular value decomposition, we're only taking the first n of those vectors to produce our reduced basis. Our reduced basis. So that's V. So V is now an array, a matrix that has as each of its columns those solution states from the SVD. Once we have done that, we're not going to jump right to the online phase. Again, we want to make sure that the online phase is independent of anything that is 10 million degrees of freedom dimensional. So we have to pre-compute the systems of equations that we're going to need during the online phase, which is effectively each of these stiffness matrices, but now represented in that reduced basis. And there's actually quite a straightforward way of doing that. All we have to do is, once we have this matrix, is we have to pre-multiply it by that matrix transpose and post-multiply it by that matrix itself. Yes? And that's the way that the strategy for reducing this k into this k tilde, where this one was big N times big N times big N, and this will be small n times small n. Because V is going to be big N times small n. Yeah? So we have N times N. And transpose is going to be N times N. So the result is going to be N times N. Now I hope this kind of reminds you of what you've done for the previous project. I actually noticed that a whole bunch of you wrote out the computation of the new reduced stiffness matrix simply as a bunch of loops, and that is perfectly fine. But what those loops end up being is simply this matrix multiplication. I encourage you to have a look at the equivalence here. So for the modal decomposition project, you would also have a vector here that involves the different modes. And well, I told you that the stiffness in the mass matrix Ij was equal to the basis. I forgot the direct equation, but you had a sum over the different components of the modal basis multiplied by the different parts of the mass, the original big mass matrix, and that whole multiplication strategy is exactly the same as this matrix multiplication that I'm showing you. Yeah, so in terms of implementational detail, this is obviously much faster. Okay, so at this point, we're finished with the offline phase. We've created our reduced basis, and we've created all the components that we need for computing the sets of equations at each new parameter point, which means that we can move forward to the online phase. We have a parameter point, we have the information from the offline phase. So the first thing we do is, given this new parameter point, we will assemble now the reduced basis system, which, well, it's still the affine decomposition, with still the same functions, theta as a function of the parameter points, but now multiplied by this reduced matrices, the reduced vector. And those are very small matrices and very small vectors, so that's perfectly fine. Now this is going to be a very cheap operation. It's going to be completely independent of that big N. Secondly, we're going to solve that reduced system. Now this is all, again, only going to be a small n by small n system of equations, so also solving this is going to be very, very rapid, very quick, and it's going to be dependent on the small n, not on the big N. All the big N is in the offline phase. And lastly, we need to do some sort of post-processing. Now, if we actually want to see the complete solution, just for visual purposes, then we have to compute the big N dimensional vector, which we can actually, again, in a very similar sense as the way that we reduce the stiffness matrices, we can do by multiplying our n times n vector here by n times 1 solution state. Yeah, so this, again, this is an n times 1 n vector. I think this is an n times 1 vector. So the solution that you get only has small n components, each of them representing the weight of the associated bases here. Yeah, so you can compute this. In principle, this is going to depend on the big N, which is something we don't like. So in really pure reduced basis methods, you wouldn't do this. But we're interested in seeing the solution. We want to see the actual solution. So that's why we will do this just for plotting purposes and because we're interested in what does it look like. In more pure implementations of something like this, you would skip this step. This would be not done. You want to only get some sort of output, and that might be an average temperature or a traction along a surface or a load at a certain point, or see if a certain deflection is larger than something. And that only depends now on this reduced vector in a very cheap way. Yeah? And actually, I'm also asking you to do something like that during the project, but I'll talk more about that in the next lecture. Okay, so this is the general strategy of reduced basis methods, where again the real emphasis lies on the separation between offline and online. I would like to see you do this as well in your code, in a sense. Yeah? So I don't want to see that at each parameter point you're reassembling the complete. You're redoing this step, because that's not the objective. The idea is that at each parameter point you can actually reuse these components that you've pre-computed, so that you can do that cheaply. Okay, then what is the actual project? So I think at this point you've really fought your way through most of the difficult things. Well, I don't know, maybe difficult is not the right word here, but the most time-consuming or the most busy work kind of things. And from now on it's going to be, I hope, just more fun and less strenuous work. Doesn't mean that this is going to be a short project, but I'll ask you to explain less things. I think everything that you explained in a previous project applies to this project and will apply to the next project. So that's why I really want to make sure that everybody has an idea of the theory that underlines that. And the project before that was about making sure you understand the code. So for now you understand most of the underlying theory and you understand the code, so we can actually use that knowledge to do some fun stuff. Yeah. So what we're going to do is we have a design optimization objective. We have the same structure, the same block. I'm going to think of this now as a temperature shield, or how am I calling this? Now some block with some sort of thermal resistance. And the objective that you'll have is to optimize this structure in the sense of changing its thermal conductivity in each of the different blocks. So we have this omega 1, omega 2 and omega 3, and you'll have a different kappa which represents the thermal conductivity in each of these different blocks. So those are the parameters. And another parameter is going to be the temperature at the inflow. So this is going to be the inflow. And what I want you to do is to create a reduced basis method and optimize that design in the sense of changing those thermal conductivities in such a way that we have the smallest average temperature on the inflow boundary for a given heat influx. And of course I'm giving you the details in the text below. So the output of your simulation state should be the average temperature. So U is now a representation of temperature, and the normalizing here by the width. So we get sort of the average temperature on the inflow, and our parameter space is going to be our inflow heat, the heat influx, and the different conductivities in each of the different blocks. And I think I have, yeah, okay, sorry. And as you see here, each of these thermal conductivities, they lie in a certain range of possible values, from 1 to 2, from 1 to 5, and from 1 to 2. And I want you to explore that parameter space using your reduced basis method, and then later on towards the end I specify the objective that you have, the design optimization, where I actually say, well, suppose that these connectivities actually depend on one another according to these relationships. What would be the optimal values to minimize that heat, the temperature at the left boundary? And so there's a difference between the temperature and the heat influx, as you'll see in this project. So I'm guiding you through the way that you would create a reduced basis method for this. We're going to start, just as illustrated in the last slide, by creating this affine parameterization or affine decomposition, where you get different stiffness matrices for each of the different parameters. And in our application is actually simple multiplication with the parameter values. So I'm talking about here about compliance. We can skip that for now. I'll talk about that in the next lecture. So you create a snapshot matrix, so you explore the parameter space. I'm giving you the points that you can use here to explore that space. So we're going to take for our heat influx, we're going to use the values 1, 2, and 3. For our kappa, we're going to, our first thermal conductivity in the leftmost block, we have 1, 1.5, 2. And these are multiplicative in a tensor product sense, right? So we end up getting 243 different parameter points. So at 243 different points in the parameter space, you have to solve the true problem. So that's the offline phase. It's going to be an expensive computation. Depending on the amount of elements that you choose, that might take, I don't know, 30 seconds to a couple of minutes. But this is already to illustrate that this can get very expensive very quickly, and that's why I want to do this in the offline phase. After that, you'll use this knowledge from the snapshot matrix to create a reduced basis method. Matlab has this SVD function. That's, as we talked about today, is what we're going to use. Then you create the reduced order system. So at this point, what we have done, we've gone through the first step. That's the affine decomposition part. We have explored the manifold and created the reduced basis method, and we are pre-computing the components of the reduced basis system. That is this step. And after that, you have created the reduced basis method, and I want you to do the design optimization. That's not specifying exactly what I would like to see there. So there's going to be 4 theory questions. I think one of them is really only real theory. The other one is just asking you what you're observing, and then the last 2 are going to be about some sort of computational time. I want you to have a feel for what is expensive here, and what is cheap, and what is the kind of time that we're saving. Yeah? So those are the theory questions. Okay. Lastly, again, I'll give you a new template, a Matlab template. Oh. Go. So I'm giving you a new Matlab template. Clearly it looks very, very similar to what we've done before. So again, I have a section here where you can add your code. I have plotting functions. And right now, the way that I structured this is I've written the code in such a way that you actually get the individual stiffness matrices and the individual force vectors for each of the different squares. Yeah, so those are the blocks that you'll need in the affine decomposition. So you already have that all set up. Yeah, so in the first function you already get the stiffness matrices for each of these guys. So what happens actually if I run this? I'm not sure. I think it should plot something. Let's plot it on a different screen. Yeah, okay. And the way that the boundary conditions work is that we're still setting the temperature to 0 on the right boundary, and is this the right button? I don't know. Use Matlab very little, as you can see. I think that should be it, right? Hello. Yeah. Okay. So we're setting the temperature to 0 on the right, and we have some sort of heat influx on the left. And I think I still am asking you to change the code a little bit to change the boundary conditions. But that's the general idea of the project. I think it really well represents the theory that we're trying to address here. I hope that with this lecture, which is actually not as short as I planned it to be, I give you a good introduction to the SVD approach and the way that we sample parameter space and reduce that into the most important components. And I'll go into more detail about how it actually works, the errors associated with that in the next lecture. Okay, so good luck, and I'll upload this hopefully today still.